The next thing that we're going to do is run through, is it 4 or 5? I think it's 4. 4 different laws that you will be responsible for within the gas laws unit. So the first one is going to be Boyle's law, which is the relationship between pressure and volume. So there's 4 key variables that we're going to be talking about with gases, and that is pressure, volume, temperature, and moles. Now, the SI unit for pressure is atmospheres, the SI unit for volume is liters, the SI unit for temperature is kelvins, and moles are just moles. When you're doing these laws, the volume and the pressure can kind of be in whatever unit you want, but no matter what, temperature always has to be in kelvins. So something that I like to do is just work with everything in atmospheres, liters, kelvins, and moles, just so that I get used to it and it doesn't feel random when I have to kind of remember which unit it'll be. So what happens is that we've got these people who were experimenting to develop theories around how gases behave. And so the first relationship that was examined was the relationship between pressure and volume. So out of these 4 key variables, they were examining the relationship between pressure and volume. So they made sure that temperature and number of moles stayed the same. So they kept 2 variables constant, and then they looked at the relationship between the other 2. Now, instead of me kind of going through and showing you on these pictures what's happening, I'm going to just throw this quick little video on Boyle's law up.
In order to understand the mechanisms of breathing, it's important to understand the relationship between pressure and volume. This is explained through Boyle's law, which states that the pressure of a gas in a closed container is inversely proportional to the volume of the container. What do we mean by this? If the size of the closed container is decreased, the pressure of the gas inside the container increases, and that if the size of the container increases, the pressure of the gas inside the container decreases. Imagine a gas, shown here as blue molecules, inside a cylinder with a movable piston and a pressure gauge. If the piston is pushed down, the available space inside the cylinder is reduced, which compresses the gas. This means that the same number of gas molecules have less space to move around in, with the effect that they strike the walls of the cylinder with more frequency. If you observe the pressure gauge, you'll see that the pressure doubles as the volume is reduced to half. Conversely, if the piston is pulled up, the available space inside the cylinder is increased. This means that the gas molecules have more space to move around in, with the effect that they strike the walls of the cylinder with less frequency. In this case, as the volume doubles, the pressure is reduced to half. And it's these differences in pressure, caused by changes in lung volume, that allow us to breathe.
All right, so summarizing this, when Boyle was examining the relationship between pressure and volume, they found that when the volume was decreased, so they were talking about this piston getting pushed down, the pressure inside of the container increases. Whereas if we went the opposite direction and said, okay, this time we're going to increase the volume of the container, then the particles hit the sides of the container less frequently, meaning that the pressure decreases. We call this an inversely proportional relationship, and we state that volume is inversely proportional to pressure. Now, what does that mean for us? Well, we want to develop a mathematical relationship. When you're talking about an inversely proportional relationship, you would say that volume is proportional inversely to pressure, meaning that as you increase the pressure, you're dividing by a bigger number and your volume would decrease. Now, we don't usually use this symbol. This is the proportionality symbol, and instead we like equal signs. So what we do instead is we replace it with an equal sign, and then we say that volume is, and then we put in this K, which is a constant. For this example, it's going to be a constant value when temperature and number of moles is constant. And we can say that volume equals K over P. So it's not that it's 1 divided by P, but there'll be some constant value K that you'll be able to divide by P to solve for volume. Another way of writing that is that this constant K is equal to pressure times volume. And now with this relationship, this constant K, we could say that two K values are going to be equal to each other when you have constant temperature and number of moles. And so we can say that P1V1 equals P2V2. And we call this the Boyle's law equation in its two-state form. So all we're saying is that you can use this equation when you're changing from a situation where you have the pressure and the volume, and then you'll have either the pressure or the volume, and you'll want to solve for one of the two. Now, like I was saying earlier, standard units for pressure or atmospheres and volume or liters. In this two-state form, the units just have to match. They don't necessarily have to be in the standard form, but sometimes it's nice practice just to make yourself always put them in that form. But just know that it doesn't matter for pressure and volume what units you're in as long as you use constant units. So here's an example you'll be asked. A sample of helium gas occupies 12.4 liters at 23 degrees Celsius and 0.956 atmospheres. What volume will it occupy at 912 millimeters of mercury? So we've got a scenario here where our pressure is changing, so our volume will change. We are going to be using P1V1 equals P2V2. They've given us that the V1 is 12.4 liters. They've given us that the P1 is 0.956 atmospheres. Then they said they want us to solve for V2 when the P2 is 912 millimeters of mercury. Now, like I was saying, it doesn't matter what units you use for pressure in this equation, but they have to match. And the nice thing is that if you just always go to atmospheres, everything's going to work out. So let's convert the millimeters of mercury to those standard units of atmosphere. So millimeters of mercury are going to go on the bottom, atmospheres are going to go on the top, and we know that 1 atmosphere is equal to 760 millimeters of mercury. So we're going to plug into our calculator 912 divided by 760, and we get to 3 sig figs, because this is an exact value, 1.20 atmospheres. Okay, so now depending upon your comfort level with math or your joy of changing equations around, when you're using this equation, you can plug your values in now. You could plug in P1 is 0.956, V1 is 12.4, P2 is 1.20, and then you can solve for V2 after. Or if you're someone who's comfortable with algebra, we know that we're solving for V2, so we could divide both sides by P2 and say that V2 is equal to P1 V1 all over P2, so that I can just plug the numbers into the formula and do it in one step in my calculator. So I'm going to put in 0.956 for P1. I'm going to put in 12.4 for V1, and then I'm going to put in 1.20 for P2. So 0.956 times 12.4 divided by 1.2 gives us, to 3 sig figs, 9.88, and make sure you answer with units, so 9.88 liters. Now again, if you didn't like that rearranging, you could have put the numbers in up here. So 0.956 times 12.4 is equal to 1.20 times V2. And so then if you wanted to, you could multiply those together and then divide by the 1.2, but you're going to get the same answer. We're all going to get 9.88 liters. Awesome. So that's Boyle's law. So go and practice that law before we move on to the next one.